when I was asked to give the presentation on automation, I've thought a little bit about it, but then I thought maybe it's just too little, too singularity, because I want to talk more about the overall thing around it. I think automation on its own is not something we die for. There should be a purpose for automation. And as a company like Yuen, we have to survive. And why do we need automation? Because we want to survive. But we cannot just survive based on automation alone. And that's the reason why I want to talk a little bit about the roadmap and technology uplifting, to all of you regarding, what is facing Hong Kong at this moment and what are we going to do in the future. So in order to look a little bit forward, I think we have to see what the future will be like. How do we anticipate it, and what do we do as a manufacturer or a company or designer to embrace it? So basically, I thought a little bit about not having big vision or whatever. I just contemplate a little bit about what the future would be like. So these are the 5 things that I have dreamt up, and I think these are very likely to happen in the future, and it will continue to happen. So first thing that you can look at is product miniaturization. And I think a lot of products are getting smaller and smaller because of the requirements of space and lack of energy to operate it. So it will be getting smaller and smaller. It means that things have to be more precision and more precision. So precision engineering will definitely be a hot topic in the future. Okay, so this is something I anticipate that I have to build my team towards this area. The other thing is high-speed data communication. I think you always find people saying, well, it takes so long for me to download a film. So preferably they want to download within 1 microsecond. That is the kind of voice coming from the consumers. So the data communication business, so to say, is one of the key areas in the future too. And thirdly, environmental equipment. Definitely, it will be one of the hot topics. Why? Because environmental problem is indeed a big problem. So how do we go about it? We can make ourselves more environment friendly, our habits more environment friendly, but also from the manufacturing point of view, we should try to make equipment that can serve this market. So this is another dream that I have, is to make something more in that area. Medical equipment definitely is a hot topic because people are getting old age, regardless of whether you're in Japan or in Hong Kong. And by 2020, I think 1/5 of the population in Hong Kong will be over 65, I think 65. So that would be a big market regarding all the accessories and equipment for helping the old age. And lastly is automation. Automation is necessary because of indirectly from the old age problem, because we don't have enough laborers. And because it's expensive, labor cost is expensive. There are many reasons for automation to happen, but automation doesn't happen alone, as I said to you before. Okay, so I will explain more in the coming slides. So our business in Yuen. So we try to help our customers to solve their problems, looking from the eyes of our customers, trying to find out what their problems are and help them. Not our problems, but their problems is what we do mind. And our business areas include all the green sentences, like the watch cases and bracelets. This is some of the old industry that I've been working on for 50 plus years. So this is the first industry that Jiangping started the business of Yuen. And secondly, new material application is something that we want to further on, because new materials is a must. If you want to go for precision and more sophisticated applications, new materials is really necessary. Precision engineering, as I said, it will be getting more and more popular. Sensor is one of the things in the upcoming future. I think most of the things in the future will have sensors. Why? Because we want to save money, we want to save time, we want to save a lot of space as well. So sensors will be one of the key areas, and which is something that we're working on too. Automation processes and equipment, we definitely are working on that, not for external use, but for our own use, because we have about 5,000 workers and want to reduce the number of people down to a reasonable level. So automation process is a must, and we can help ourselves. Maybe later on we can help others as well. Environmental equipment, we know that we generate a lot of scrap and a lot of environmental unfriendly stuff. So how do we help ourselves to clean it up and also help the industry to clean it up? That's why we make also this kind of equipment that we'll show you later on. Medical healthcare devices, we are very much concerned about the large number of population, especially in China, who wants to medically diagnosed for the kind of diseases they have. And this is something that we have to cater for, the whole mass, the population, not only a few rich guys. We have to cater for the mass media, the mass people. And the industrial technology part, again, is the part that I talked about before about the data exchange. It has to be high speed, very high speed, mega high speed. And we are working with products on data exchange center, data exchange equipment. We are supplying that too. So we are actually catering for these as well. So what's the mission of our R&D center? Actually, it's to provide one-stop customer focus and value creation for companies who come along and ask us to work with them and help them, upgrading their productivity, quality, technology, service management to achieve and exceed the world-class standards. Actually, why do I put this in? It's not something that we are very proud of or bold about. It's something that is a prerequisite. If you want to compete, there's no secondary anymore, no tier 2, no tier 3. I think if you look at the world nowadays, people are trying to separate. They don't want to combine or work together. You can see Brexit, and you can see what's happening with Trump. People want to retain their own jobs. Why? Because of the fact that people are afraid of competition. But without competition, we will never get new jobs. So competition is prerequisite. We can't avoid it. That's why if you want to get a job, I think you have to be better. Our vision is to be a good provider of consultancy service related to materials, chemical technologies, as well as related to manufacturing of products and parts. Watch precision part, healthcare, environmental, automation, machine design, and manufacturing, leading to world-class manufacturing is what we are striving for, okay? Our team, our R&D team is not, it doesn't contain a lot of people. It has less than 50 people, but we all need very good people in our team. We don't want a lot of people, but we need people who are really keen on doing R&D. So basically, we have, you can see that 4 blocks. The main thing that you have to look at is applied R&D. We are not doing R&D for the sake of publishing papers. We are doing R&D for the sake of, getting into the market. And we have identified a few key areas that we focus on. One is materials technology. Whatever you do, whatever industries you are in, at least in China or Southeast Asia, you really need to understand your materials and how to apply it. So we have our own R&D lab with a lot of analytical equipment, helping us to do various things like reverse engineering and product design, etc., etc. Failure analysis, of course, Simulation modeling, this is one of the key areas that I think is missing quite a lot in Hong Kong, and I think this is very crucial. Whatever project we start with, you don't start with making a product and test it. Actually, you should start with brainstorming and finding out the ideas and and make sure how it works and whether it really works or not by doing a lot of simulations, virtual reality, to make sure that what you intend to make or to design and make actually works out before you go and make your prototype. You don't do simulation to prove your prototype. You do simulation to get your ideas at the beginning before your prototype is born, okay? So this is why we're so concentrated on. I'll show you something about this in due course. And then automation is the part that I will focus to talk a bit more about. It's basically to do automation in a factory. You don't go and buy machines and use them in your factory right away, because then you can't really do much automation. Automation can only be done if you actually do lean manufacturing first. Before you can do lean, forget about automation because you're wasting money. So first of all, you get the lean done, and then you can go for automation. When you do automation, you should not do automation of a complete line. You press a button from one end, you get something out of the other end. Yes, you can do it, but it's very expensive. But it will become obsolete very quickly too. So what you have to do is to build some building blocks, and you make a small automation module, and then, with which you can combine together to form your big cells and big automation lines. Okay, and we can't do everything with my own team, of course, because there's so many things that we need to seek help, and we don't know, we have no equipment. So we try to cooperate with local and overseas research partners. This is one prerequisite. You work together, then you get something that we can share together. Okay, our lab, as I said before, we use our lab to do raw material assurance. reverse engineering and failure analysis. These are the day-to-day stuff that we do, apart from doing material research and product design. So I'll show you one example of what we do. I think you know what these means, material assurance and reverse engineering. Reverse engineering, you want to do something, you just buy one and then you dismantle it and then you analyze everything in there and see how they are made and how they combine together. It looks easy, it sounds easy, but it's very difficult to do because there are many things inside that you can't see just by dismantling it. But anyway, that's the first step. Okay, something to share about this case. We have machines which failed, keep on failing. We have very large boats here. And you're talking about M30, something like that really big boat. And it fails, it keeps failing, all of them. You're talking about 16 of them. And we don't know why. We went back to the design and couldn't understand why it failed. It has worked for a while, but it still failed. So we took the bolts in and analyzed them one by one. And we took the hardness. It's very simple. We just took the hardness. You found out the hardness was actually, something like 32 to 40 HRC. But we thought we were buying the 12.9 bolt. We should have a 38 to 44 HRC. So actually, we paid for 12.9, but we got 10.9. So actually, we have been cheated. But these guys don't know. They still keep using it and they put it in their machines and that failed. So we only find out that once we got this failure and look into it by analysis. So this is a pretty bad thing. And after that, we had to change all the bolts in every machine in the field by using the much more qualified bolts. Okay, so this is one example of how we use the lab to help us to prevent problems. Okay, precision forging. Precision engineering is very important, as I said to you before. Precision machining, of course, is very important. That if you have the money, you buy a really big machine, great machine like a Bumotech, and probably got pretty precision out of there. But people don't just go for precision machining anymore. They want low cost. So how do you make something low cost? So you don't do machining from the beginning. You do forging first. Once you've done a near net shape forging, and then you do machining. So the cost will come down. Outside here, outside in the market, it's very competitive. You're talking about cutthroat prices. If you don't do this kind of approach, I don't think there's a chance to get a job. So in our own watch cases, we actually do a lot of simulation as well to do a forging. Before we do the simulation on the forging, so that we can save a lot of wasted material. So forging using simulation first is a routine way that we are doing it now. Because if you don't do analysis, you forge something out and then you get a lot of these flashes, and there's a waste of time, waste of material first of all, waste of manpower, to take it off, to trim it off, and then the grinding. You have a lot of grinding going on, rough grinding, fine grinding, and so on. So what do we remove the material right at the beginning when you do forging? So that is the philosophy. You save right at the beginning. And this is another example of making a hub. So again, let me explain what it is. What it is first. Basically, we want to do a hub like this. When we did this, we have not this done yet. This was only on the drawing. So this is only half of the blank that we're using because this model is axisymmetric, so we just take half of it. And we use the elastic plastic model based on the material that we make this hub. So we know the elastic plastic curve, and then we feed into the computer and then do this simulation. We actually found out that at certain points it's not so easy to figure out that it will work. Only after the simulation we find out that it should work, and then we make the tools and then do the actual tool to make the hardware. So I show you one of the example. I hope it works. Okay, so basically this is a simulation half model. This is the equivalent plastic strain here. So the whole thing, the whole blank is like this, and this is a symmetry line. So you see, it's very difficult to find out if it really flows over, because it's difficult to converge here. So it takes a a lot of iterations to find out that, oh, it really does the job. So again, without the simulation, we probably will be trying, I think, maybe 10 to 22 different tools to see if it will work or not. With these, we only need to try 1 or 2 tools, to make it perfect almost. So you see the importance of simulation. Why I mention this, because simulation is part of the technologies that we deployed in our R&D center. So just to share with you what it can do for us. And this is another case of making a kind of holder. I don't tell you the customer's name, but basically this is made of aluminum. Again, we are using elastic plastic analysis and simulate it with the forging. This is done before the actual tool was made, and you can see how the thing is formed. And if the material is made too thin, because one of the part it has to be pretty thin in the final product, and we cannot make it so thin because of the fact that you get fracture. So we don't do that. So we leave more room there, and that's actually done at the end by machining. That's what I was saying before. You can't just use machining. You have to use forging plus machining as the tool, as the approach towards making a lean part, a part that saves costs. Okay, machining doesn't just involve these. You have to be able to measure it as well. I mean, if you want to know, after my machining method, I want to find out what kind of surface finish I have on the surface. You can't just say, oh, this is good enough. You look, your naked eyes look at it, it looks smooth. So that's not good enough. Actually, we measure the roughness using optics and find out actually the profile on the surface. Like this little tiny component here, we were measuring the profile on the surface. You can see that it's grind round and round and round. It's machined like this. And the average RA value is about 300 nanometer, so it's about 0.03 micron. So that's within the spec of the requirements. Okay, so this is how on the one hand, we want to do something precision. On the other hand, we want to make sure that we can measure what we have done. Otherwise, you cannot say that you're precision. So this is the way that we are moving forward. And these are the parts that we make. Apart from watch cases, we also make high precision parts as well. Okay, so these are different business areas that we are embarking on. Okay, now I'm coming back to some automation cases that I want to share with you. So automation on its own is not just with a piece of paper and you write down, draw down what you want to do, because there's so many things affecting it, like the precision. How do we control the precision? It's not just to buy a very accurate servo motor and so on and so forth. All the structural bending and deformation has to be included, it has to be thought through. So you have to basically do a structural analysis to find out if the thing, at the end of the day, at the tip of the finger can maintain, 0.02 millimeter precision, let's say, or 0.01. Why? Because if you want to make a watch case, that precision has to be within 0.01 mm. So the way that you position it, put it in the chuck, has to be more accurate than that. Otherwise, you can produce something within 0.01 millimeter. So this is one of the pick-and-place machines I want to share with you. We have a lot of these machines in-house, because they are pretty old machines, 10, 20, or 5 years. But my boss asked me to automate it, but you have to use the old machines. So you just have to add something onto it, a pick-and-place arm or whatever, but low-cost one, not expensive. So I got the job, and then I had to go through and look at it and find out how we do it. And this is the result. Basically, this is a automation process that we have made ourselves from design to manufacture and communicating with the NC machine, the turning machine. So the mechanics is done by ourselves, the software was written by ourselves, all the electronics and controls were made by ourselves, okay? So it's gonna take a bit long, but basically, now you pick up a watch case and then you come here and then you wait until this is finished. So our time to pick up is very fast, but the process inside is very slow. And so we can't do much about it unless we can speed up the production time, the cycle time in here. Okay, you see that it's picking up, pick out the finished one, and then clean it, and then come down again, and then put the unfinished one, the one that just picked up in here, and then you start working, and this guy will come up to pick another one. So this is what we call a module. We are not automating the whole line in one go. We're actually making a module and combine them like Lego, depending on the combination of different machines, whether you use a lot of NC machines or CNC machines, okay? So that really depends on the lean manufacturing process or how you go about doing it. So then you may ask, how do we guarantee that the machine is good enough before we make it? So that's done by means of, as I said to you before, simulation. So actually we do a lot of simulation before we actually make the hardware and test it in-house. And before we bought the components and assembled them together and assembled it and tried. So actually what we do is that we look at the stresses to see if they're all well below yield stress. And also the most important thing is the position, the final position of the arm. Does it come to reach the precision that we require? And also we look at the frequency of this analysis as well to find out that it doesn't vibrate due to resonance or something. Okay, so we do that, and we have used this method many times to work on even CNC machines. Just now what you saw was the NC machines. These are CNC machines. We have maybe something like 500 machines of this kind. So we have to automate all of them. So basically we just run through the same philosophy and approach and inform our own automation line. If you look at this one, I can show you what it can do. It works. Wow. Oops. So this actually was taken in our trial run. So, oops. So it's an automation again on picking up watch cases, put it in our CNC machines. Okay. So pick it up, go over here, position it, and then we move up and wait at the window, and then we go in. Inside there is the CNC machine. Okay. And we come back. And then go in again. It goes in and out because we want to clean the chamber, clean the shop without ruining our robot arm. So you see that these watch cases do not have to put in a particular direction. It can be put on any orientation, and we can handle that. This is the first version, and we are developing other versions now, which are more sophisticated in picking up watch cases. Here, this is the CNC side where you do the machining. Okay, I think I don't want to get you bored. I will continue with other slides. Some industrial cases I want to share with you is the equipment, environmental equipment. You know, because we do a lot of machining, we produce a lot of scrap. And how do we deal with this scrap? And you see, this scrap is very messy and getting in anywhere. You need a big storage to store it up. So we have thought of compressing this scrap into neat little cake and be able to store it nicely like this and not like this. Okay, this is the machine that we produce, and we are now already selling it into the market. And this machine basically is like this. You put in scrap material, and then you have a shredder here, and the shredder, after shredding, the bits will come up here and put it into this compressor, pneumatic compressor, and then you will press it and form a cake and come down here. Okay, so so actually when we make this machine, we actually did again a lot of final element analysis to safe proof the integrity of the machine before we actually make the hardware. And when we do this analysis, we actually simulate the preloading of the bolts as well, so it's very accurate. You preload it to the way that you should in the design book, and then you find out if the machine will fail structurally. So whenever you get high stresses, you reduce the stresses to make sure that your machine have a low average stress, so that it won't early failure by fatigue. Okay, another case, XYZ handler, which are focusing on the diagnostics market. You've seen people doing diagnostics, test tube in the lab, and that's done by one person at a time. So that takes too long. So we're going to have this mass diagnostics platform where you put a lot of test tubes in here, and then we have an XYZ liquid handler, which goes in and pick up some liquid and go into radical another test tube, and then release the liquid in that test tube, and then mix them up together. So with that, you're able to program most of the tests inside the equipment, and then do a lot of tests at the same time. Okay. What is our objective at the beginning? The initial objective was that people were making these kind of machines, but only with 4 channels. They have 4 pipettes doing this injection at a time. So we increased that to 8 channels because we want to double the speed, the throughput. This is the initial product that we designed ourselves at the beginning from a piece of paper. So how do we know that this is going to work or not? So again, we do a lot of final element analysis to safe-proof it. First of all, there's the deformation analysis to find out if it just deforms too much. Okay, I think 2 mm is the maximum, the tip. And then, of course, the stress analysis to find out if there are any high-stress regions that would go plasticize. We have made this analysis. And then lastly, the frequency analysis. We have to make sure when it moves, X series, D series, it won't vibrate. Because if it vibrates, then customers will not accept it. So this is something that I want to show you. It's quite interesting. It's coming from the modeling, the design modeling. Oops, this is not working. How do you fix it? Oh, I think it's doing auto-saving on a big file. It will take some time. I think it will take some time because it's doing saving. Auto, I think it's good. Auto recovery. Okay, good. Okay, the machine that you saw just now, this is still in the design stage. We haven't made the hardware. You see that it's trembling. It's actually vibrating. You see? So it definitely has a problem, The customers won't accept it. This is all done by analysis. You see that it's really trembling. No, there's no one will accept it. So what we do then, we improve it, modify it, and try to reduce the vibration. And this is what we got. So basically, it doesn't vibrate anymore after tuning some parameters. So again, this gives us a window of improvement by way of getting an idea, prove it using simulation. And at the end, we find out that, it works in simulation. Then we are confident that we can go ahead to make the hardware, just to save cost. This is what we have manufactured at the end. So actually, we make our own pumps. We made our whole machine. This is the whole thing that we make ourselves. Okay. Again, this is also a direction towards automation, because this is actually for enabling the diagnostics world to be able to do a lot of tests, mass tests at the same time. So this is also kind of automation, but it's external. Okay, we got some patterns outside, so I just want to show you. Just an example, we've got some patents awarded, and back in 2006. Okay, I think I just want to end this presentation by saying, innovations can make a big difference to our commercialization and for our dreams to come true. So thank you very much. If you have any questions, you're welcome.